are now going to transition from elements into minerals. Elements make up minerals. Many of the elements that we have talked about already are even considered minerals by themselves, and we'll learn that next week. But first, let's talk about what a mineral is. A mineral is a naturally formed inorganic solid substance that has a definite shape or structure and is also crystalline. So let's break down those words. Let's look at that. That's a really big sentence. So let's break down each word so it makes sense to us. The first one is natural. Okay, it's found in nature. It's not man-made. So that's something you can write down. That's something that you can think about. It's not man-made. It's natural. It's found in the environment naturally in nature. The second word is inorganic. Inorganic means it does not have carbon and hydrogen. It's not made from a living thing. It wasn't once living. So it can be maybe just sodium, or it could be salt, sodium and chlorine. There's no carbon and hydrogen in it. Sugar would be organic, so sugar would not be a mineral. Salt, however, would be a mineral because it does not have carbon and hydrogen. Now, diamonds and graphite are considered minerals because they just have carbon in it. So we're looking for if something is organic, it has carbon and hydrogen, it was once living or part of something living, so that would not be a mineral. Okay, so looking at that word inorganic, not living, not having carbon and hydrogen. The next word is solid, and that ties in with having a definite shape. If something is a solid, that would be considered a mineral. So mercury, it is a liquid at room temperature. Mercury would not be a mineral, even though it's an element. Another great example, a lot of scientists kind of argue and debate about this, is ice. Well, at room temperature, ice is liquid water. Ice can be in crystalline form, but at room temperature, it's liquid. So technically, ice or water would not be a mineral. And the last one, we talked about definite shape. So that ties in with a solid. It keeps its shape at room temperature. The last one is crystalline. It has crystals, and we'll talk about what a crystal is and how a crystal grows. And so something that has a crystalline shape or structure, it has different sides or faces called facets. We'll talk about that in a little bit. And as it grows, it just not only just gets bigger, but it's replacing atoms on the outside. Now, a crystal can actually grow in different ways. It can actually grow from being dissolved in water and growing out of the water. In elementary school, you may have done a project where you grew crystals, like maybe sugar crystals, where you dissolved the sugar in the water and then you put a string down into that water, and as the water evaporated, basically the sugar little crystals grew and got larger and larger on the string. Another way in which crystals can happen are from the cooling of magma. So if magma cools very quickly, and we'll talk about this when we learn about the rock cycle, as magma cools very quickly, there probably will not be crystals. But the slower, this is very important, but the slower magma cools, the more crystals grow and form. So if you have a volcano and it cools very slowly, or maybe magma is under the ground, it forms very slowly, then basically you're going to have lots of crystals forming. Okay? If magma cools very quickly, no crystals, slowly, more crystals. So let's take a look at what I just kind of talked about. You can see there the natural processes. It's not man-made. There's the two types of ways crystals can be formed by the cooling of magma and being dissolved in water. Then we have the little spiel about something being inorganic, not being living, not having carbon and hydrogen. Then what is a definite volume and shape? That's a solid. It can be an element or a compound. And then at the very bottom here, what is a crystal? So let's look at what is a crystal. They grow, and how do they grow? And this is actually called accretion. This is when the atoms of minerals are added on top of each other, allowing the crystal structure to grow. Now, each mineral tends to have a distinct crystalline shape. There can be many different shapes, more square, there could be longer ones, different forms, different sides, and these sides or these faces are called facets. Now, there's four main properties of minerals that we're going to focus on. There are some other ones, but we're going to focus on the top four. Luster, which is not really shininess, but it's reflecting light. Then we have hardness, how hard something is. If something is very brittle or very soft, it would have a low hardness. If something is maybe the hardest, most likely it will scratch everything. So we're looking at something soft, it most likely will be scratched. Cleavage is one example of breakability. Breakability is actually what we're going to be focusing on. And cleavage is the type of breakability in which it breaks evenly. It separates on even, smooth faces. While the other side of that coin would be fracture. Fracture is different, is the opposite of cleavage. Fracture would be not even. It would be more jagged and less smooth. So that's how an object is going to break apart. And then number four is streak. Streak is referring to the mark, colored mark it makes on something. So most likely a brown mineral will make a brown streak, or a gold mineral will make a gold streak. But that's not in all cases, and we'll talk about that. Now there's another example that maybe the textbooks use, and that's color. Color is not a good way to identify minerals due to the fact that quartz has many different colors. So we can't say, look for this color and you'll know it's quartz. You can't do that. Another example is mica. Mica has different colors, and therefore it's identified as different types of mica. So color would not be a main way in which we can identify certain minerals. It may help us create subcategories, but it's not going to be the best to identify. So we're going to focus on these four. So here we have luster, the way light reflects from the surface of a mineral. There's two types of luster: metallic, does it look like a metal, or non-metallic. It still reflects light, but it doesn't look like a metal. It can still be shiny, okay, but it doesn't look like a metal. So pyrite, fool's gold, has a metallic luster, while sulfur, it's still shiny, it reflects, but it does not have a metal reflection. On the right is a basic example of the Mohs scale, going from 1, which is very soft, to 10, very hard. Talc, that's one you're going to have to know, which is actually ground up to use baby powder. Here's another picture of the Mohs scale, Mohs hardness scale, and you can see as things move down, okay, they get harder and harder. And so basically we can use different things like, can it be scratched by a penny? Can it be scratched by a nail? Okay, can it be scratched by your fingernail? Can it be scratched by a metal nail? So you can see here's gypsum, very soft, can be scratched by the fingernail. Then we have calcite. It would scratch the fingernail, but it can be scratched by the penny. So the fingernail can't scratch it, cannot scratch it, but a penny can scratch it. So a penny's a little harder, showing that calcite is harder than gypsum. Then we move to fluorite. Fluorite, the fingernail cannot scratch fluorite, the penny cannot scratch fluorite, but a metal nail can scratch fluorite. And then the last one, diamonds. Diamonds are the hardest. So diamonds will scratch all of those and cannot be scratched by the fingernail, the penny, or the metal nail. Okay, here's breakability, in which we talked about cleavage. So you can see cleavage is referring to breaking along a smooth, flat plane, while fracture is more jagged or random. So you can see the two pictures. At the bottom left is mica, and mica breaks off in flat layers. You're going to look at that in one of your labs. And then you have quartz, very jagged, okay, jagged edges. Okay, here's streak. We're going to be looking at some streak plates. If you look at chalk, red chalk makes a red mark, blue chalk makes a blue mark, white chalk makes a white mark. Well, that's not in all cases. Pyrite may have a more of a goldish color to it, but when you do it across the streak plate, it will give off a black or dark green color. Okay, so we say we're not going to focus on color because certain minerals may have different colors. Another example is fluorescence. Fluorescence means that something will glow. Minerals give off a glow. This is based on the wavelength, dealing with ultraviolet rays. So, will it give off a fluorescence? And then we have magnetism. Some minerals are going to have a magnetic ability, and one example is lodestone. Another type is called magnetite. Lodestone and magnetite both have magnetic abilities. Okay, here's a little practice for you. As you look at the different examples, you can identify if something's a mineral or not a mineral and why. Okay, the first one, wood. Wood is not a mineral because it's organic. It is living, or once was living before we cut it down. Okay, so wood is organic, so it's not a mineral. Fossils would not be considered a mineral due to the fact that, number one, some of them are organic carbon films. They have the carbon that's left over from the pressing of the organism into the rock. Now, some fossils, basically, the organic material all breaks down and it's left with a mold of the animal in the rock. Now, minerals seep in and the moisture evaporates, and then that leaves a mineral deposit in the space that the organic material broke down and left. So that space would be called a cast, and you'll be learning about that later on. Now, why would that not be technically a mineral if you're filling in that space with minerals? Well, the mixture of minerals is called a rock. So technically, a fossil would not be a mineral because it's many different minerals together. So a fossil would be considered a rock, not a mineral. Okay, gold. Gold is a native element considered a mineral. It is a certain type of element considered a mineral. So yes, gold would be a mineral. Topaz is a compound mineral. That would be both gold and topaz because they're solid, they're natural, they're inorganic. They would be considered minerals. Okay, bones. Bones are organic, part of a living thing containing carbon, hydrogen, and so forth. So bones would not be a mineral. Plastic. Plastic would not be a mineral because it's not natural. It's man-made in the laboratory. Okay, here's diamond and coal. Diamond and coal are both made of carbon. Diamond, however, is made from carbon pressurized. Okay, diamond would be considered a mineral. It's a type of carbon. Coal, however, would not, because coal is a fossilized rock, basically fossilized from organic remains. So dead plants or animals, fossilized, that would be coal. So because it's coming from dead animals and plants, it would not be a mineral. Polyester is man-made in the laboratory, so it's not a mineral. Sugar has carbon and hydrogen. It is organic, coming from plants. That is not a mineral. Mercury, it's liquid at room temperature, so it would not be a mineral. Quartz would be a mineral. Salt, same thing. Okay, NaCl, it's inorganic. Talc, even though it's soft, yes, it's a mineral, has all those attributes. Okay, then we go to ice. Ice, no, it is not a mineral because at room temperature, okay, can then melt. Okay.